Hello everyone. In this video I'll be presenting to you a proof of the Riemann Zeta Function's functional equation using Mellin transforms. In the last video we discussed showing some non-trivial zeros of the Riemann Zeta Function using Desmos, but in this video I'll be proving to you the functional equation. And there are a lot of different proofs that I've seen before involving contour integration. This one's a little different. I think it's really nice, so I'm going to get started off with defining the Mellin transform. So I've actually seen this in a previous video that I made regarding Mellin transform and the connection between the zeta function. We'll actually be seeing the result in this proof today. Now normally you write braces and then the function, but just because we'll be using another notation for something called the fractional part of a number, using those that notation, the braces notation, I'll actually, if you don't mind, I'll be using parentheses here, so I think that's okay. So what the Mellin transform does is it takes a function of t and it outputs the integral from 0 to infinity of that function of t times t to the s minus 1 dt, where s is, well, we'll take that to be a complex number. I won't actually be talking too much of the technicalities of when this is defined as far as what values of s make this work. But what I will be doing is sharing with you some really basic properties of the Mellin transform, specifically when you take the Mellin transform of other functions. Now, what this may remind you of is kind of like the Laplace transform. The Laplace transform looks pretty similar, but as it turns out, Mellin transform is a little more restrictive, and actually a lot of the properties are actually pretty hard to show. Now, the first property that I want to mention is property of linearity. So if you take the Mellin transform of a function of t plus another function of t, you can split this up as a Mellin transform of each one added together individually like this. Similarly, if you have the Mellin transform of a constant times a function, you can pull that constant out. So this is pretty obvious why these properties are true, so I won't be actually proving these to you. But the reason why they're true, of course, is because the Mellin transform is based on an integral. It's defined as an integral, and it inherits those properties from from the integral itself. Integration has linearity properties. Okay, now the next thing is the gamma function. So the gamma function, if you don't know, is kind of like the generalized factorial. In fact, it's not kind of, it is the generalized factorial. So I'll be talking about the gamma function of s, and it is defined as follows. It's defined as the integral from 0 to infinity of e to the negative t times t to the s minus 1 dt. Now, what this ends up being is the same as s minus 1 factorial when s is an integer. When s is not an integer, well, we just say this is factorial of s minus 1, whatever s is. So for example, if s is 1/2, the 1/2 minus 1 is negative 1/2, and you can say this is like negative 1/2 factorial. In reality, it's the extension of the factorial function onto non-integer values. And in fact, specifically here, s is a complex number, so the notion of factorial doesn't quite make sense, but again, this is an extension of factorial. Now, to prove this side of things, I'll allow you to kind of do that on your own. A nice way of doing this, when s is equal to an integer like n, or a natural number n really, you can use induction to prove this. It's not very complicated, it involves integration by parts. That's all I'm going to be saying there. Now, something that I will say beyond this, though, of course, is pretty obviously, this is a Mellin transform. It's a Mellin transform of what? It is the Mellin transform of e to the negative t. Okay. Also, because factorials have this kind of multiplicative property, that if you multiply s to s minus 1 factorial, this of course gives you s factorial. Well, what ends up happening with the gamma function in mind is that this is s times gamma of s will give you the next factorial, which is gamma of s plus 1, which I'll write as 1 plus s. So that property will come a little later. And now what I'm going to do is present to you a few more properties of the Mellin transform that I'll actually be proving from the ground up using some of these facts here. The first of these properties has to do when you take the Mellin transform of a function of a number times t. So what ends up happening, and it's true because of u substitution, it's actually not too hard to see. By the definition of Mellin transform, we get f of a of t times t to the s minus 1. Perfect. So now what I want to do is I want to let u be equal to the inside, So the inside of the function is a times t. And then notice du would be equal to a times dt. And, well, notice here, t is what? T is u over a. And I guess similarly here, dt is 1 over a times du. So, applying this substitution, we get the integral of f of u times t, which is u over a all to the s minus 1. I'll pull the a to the s minus 1 out. It's in the denominator. So because it's in the denominator, we can take this as a to the negative power, so a to the negative s minus 1, which is 1 minus s. And then dt again is 1 over a du, but pulling that out, I'll kind of show it here. So we can write 1 over a, but I'll write a to the negative 1. And the powers add so that those 1's cancel out, and we just end up getting this. Now, of course, doing the trivial substitution u is equal to t tells us that this is just a Mellin transform of f of t. So in fact, in reality, we just get this. So that's the first property. The next property I want to show is taking the Mellin transform specifically of sine of t. Now, this is a little different. I'm not actually going to be writing this as an integral as you may think based on the definition of the Mellin transform. No. What we're going to do is we're going to leverage the properties that I showed you above. And the fact that sine of t, if you don't recall, can be written as e to the it minus e to the negative it all over 2I. The reason for this is because of Euler's formula. E to the it is cosine of t plus I sine of t. E to the negative it ends up being its conjugate, and when you subtract it from its conjugate, you get double the imaginary part, which is 2I sine of t, and divided by 2I gives you this. So now, if we replace that with e to the it minus e to the negative it all over 2I, well, we can apply some linearity properties to basically turn this into all over 2I, the Mellin transform of e to the it minus the Mellin transform of e to the negative it. Now, there are some specific things with the last property we saw with a specifically. In fact, a technically has to be positive, but if a is equal to I or negative I, the property ends up being true, but there are some technicalities you need in regards to how the limits 0 and infinity change. In fact, I didn't quite talk about that. I just kind of rewrote 0 and infinity. But if u is equal to at and t goes to 0, then u is 0. And if t goes to infinity, a times infinity is infinity when a is positive. Now, if a is I or negative I, well, infinity with complex numbers can be weird. We just kind of call it the 1 infinity. So it kind of still ends up being true, but there are some technicalities there that I didn't quite get into. So you can look into that on your own if you like. But regardless, I'll be using those properties here. So notice we know that, let me kind of remind us, the Mellin transform of e to the negative t is the gamma function of s. Okay? Now, this it looks similar to e to the negative it, but in fact, one way to think of it, well, I'll rewrite it like this, I guess, is it is negative it. Okay, double negative it. And what I'm really doing is I'm replacing t with negative I times t, which sounds very subtle, but really what we're doing is we're using e to the negative t to be our function of t, and negative it is basically acting as a times t. So in other words, a is negative I in this particular case. And for this next one, it's a little more obvious because we have the negative already. This is just e to the negative I times t, where I is a in this case from the property we saw on the last screen. So what we end up getting is negative I to the negative s times the Mellin transform of e to the negative t, which is gamma of s, minus, very similarly, we get I to the negative s times gamma of s, all over 2 times I. Now there's a lot in common here. I'll pull the gamma to the s off to the side, just like that. I'm also going to use the fact that a negative I is 1 over I. It's very easy to verify. If you multiply top and bottom by I, you get I over I squared. I squared is negative 1, so I over negative 1 is negative I, so that's certainly true. So with that being said, we can write this as I to the positive s minus I to the negative s. And I, by Euler's formula, ends up being e to the I times pi over 2. One interpretation of Euler's formula is that it's the polar form of a complex number. And I on the complex plane has an angle of 90 degrees if you start from the positive real axis, and its magnitude is 1. So it ends up having that polar form, e to the I pi over 2. Also by Euler's formula, it's cosine of pi over 2 plus I times sine of pi over 2. So it's pretty easy to verify that. So because of that, we can write this as e to the I pi over 2 s minus negative e to the I pi over 2s all over 2I. And exactly from the definition I gave earlier for sine of t in terms of e, this guy right here, let me box it. That guy right there. Well, notice t in this case is pi over 2s. So in fact, this is sine of pi over 2s. So this is sine of pi over 2s, or pi s over 2 if you will, times gamma of s on the outside. And there we go. This is the result. I guess I should box the whole thing, but I'm not going to actually do that because I'm going to actually write all the properties right now, and then we'll talk about how we can use this and other things that we can recall from previous videos I've made to finally show you the proof of the functional equation. Alright, so here boxed in red are all the properties we just discussed, and here boxed in green, there we go, are the properties that I mentioned are from a previous video, which I'll actually link right here in the corner for these two videos. I did one for the first property and one for the second one, so I won't be discussing the proofs of those here. They take a little bit of time. Now, recall here that this is notation for the fractional part of 1 over t. Now the fractional part, if you don't know, is just the part after the decimal of a number is kind of the best way to describe it. Really, it's the number itself minus its floor is one way to think of that. And what I'll try to be doing is try to make some connections between these two and basically kind of write, well, what essentially is a Fourier series for the fractional part of x. So I'm going to kind of do that right now. Now, to understand what's going on here, let's kind of take a look at what the fractional part of x looks like. So I'm going to graph y equals the fractional part of x. And I'll kind of stick to the first quadrant. And let's notice that really, when you go between 0 and 1, the fractional part of a number is actually itself. Up until you hit 1, the fractional part of 1 is 0. So I'm trying to draw like a open circle there. There we go. So why is the fractional part of 1 0? Is because you can think of 1 as 1.0. So its fractional part is 0. Because remember, the fractional part is basically everything after the decimal. So the fractional part of 0.9 is 0.9 itself. The fractional part of 1.9 is 0.9. So in other words, this repeats. And you essentially have a period happening here. So what this really reminds me of is kind of like the sawtooth graph that we saw from the graph of this second graph. So that's why I say we're going to be finding the Fourier transform of the fractional part of 1 over x. Basically, I'm going to try to make these look the same. I want this sum involving sine of nx over n to look like the fractional part of x, to make the graphs look the same. So if we were to graph y equals, well, that sum, what does that look like? Well, remember, this is equal to pi minus x all over 2, but in fact, this is really only true on the interval from 0 to 2 pi. So to try to show what this looks like in the first quadrant, it's kind of interesting because it actually goes below the x-axis. There we go. Well, you can kind of see the slope is negative 1/2, and the y-intercept is pi over 2. So you start at pi over 2, and then you go all the way down until you hit negative pi over 2, because the slope is negative 1 over 2, and that lands you at 2 pi. Then it repeats. 4 pi, and so on. So these are both lines that kind of repeat in this periodic way. So how can we turn this one into this one? So let's just kind of focus on one period for a moment. Now I want to notice that the period here is 0 to 1, right? Every interval of length 1 kind of repeats 0 to 1, 1 to 2, 2 to 3, and so on. So one way to do this is to kind of look at the mapping, how you turn this into the interval from 0 to 1. And of course you do this by dividing everything by 2 pi. So let's kind of do that, and let's see what happens to our sum. So if we have the sum from n equals 1 to infinity of, so you may think that I'm going to replace x with x over 2 pi, but in fact, because we want to divide the interval by 2 pi, we end up multiplying x by 2 pi, really replacing x with 2 pi x. So this becomes sine of 2 pi n x over n. And just kind of understand why this is happening is because as x goes from 0 to 1, well, 2 pi x will go from 0 to 2 pi. Okay, so we've kind of changed domains now, so x is acting between 0 and 1, much like we wanted to here in red. Perfect. So now this isn't actually equal to pi minus x over 2 anymore, because we're replacing x with 2 pi x. So in fact, this is equal to pi minus not x, but again 2 pi x all over 2. But now we're on the interval from 0 to 1 instead of on the interval from 0 to 2 pi. So the interval has been kind of mapped out, okay? And now the question is, how do we turn this into x? Why we want to turn it into x, of course, is because, well, each of these lines for the graph of the fractional part of x, really in the first period here, is the graph of y equals x. So the slope is 1 and the y-intercept is 0. So how do we turn that into x? So after looking at it for a bit, it's pretty obvious that we need to cancel that 2 in the denominator and then get rid of that pi in front and then divide by pi to get x by itself. So let me try to write this like this. So we have this. We can multiply both sides by 2. That'll kind of cancel these guys out. Then we can, I guess, subtract pi. And then after that, we can multiply everything by negative 1 over 2 pi. So the negative 2 pi's cancel out, and you just get x itself. So this would work. Now, what is actually happening to the sum? Well, let's take a look. So we got to keep track of what we just did. But this sum is exactly this guy here. Okay? So I'm going to write it like this. We have the sum of sine of 2 pi nx all over n. And let's kind of keep track of what we did here. We multiplied it by 2. Then we subtracted pi. Sorry about that. And then we divided by 1 over negative 2 pi. So if we distribute this, what this ends up turning into, notice the second term is going to be double negative, pi over pi cancels, so you just get 1/2. And then we get minus, the 2's cancel there, and you get 1 over pi times the sum. So maybe there was a better way of me handling the simplification ahead of time instead of after the fact, but that's okay. All the dust is settled now. So perfect. So this actually will give you a graph that looks like y equals x, right? It has a slope of 1 and a y-intercept of 0 on the interval 0 to 1, and it repeats, actually. So this ends up working out. In fact, this is equal to the fractional part of x. So we have done it. We've actually found basically a Fourier series for the fractional part of x. Now I'm going to write this over here next to everything boxed in green, and then we'll continue. Alright, that took quite a bit of time, but it was all worth it because now we're essentially going to get to the proof. I say essentially because there's one tiny thing to discuss, and it has to do with using the Mellin transform of 1 over t, of the fractional part of 1 over t. Okay? Now, okay, so this is equal to the integral of the fractional part of 1 over t times t to the negative, or t to the s minus 1. Yeah, there we go, that guy. Now, to make things a little simpler looking, we can actually use a u substitution. I'll actually use an x substitution. X is equal to 1 over t. It's kind of interesting because notice the derivative, dx, is going to be a negative 1 over t squared dt. And I guess, well, there's a lot of ways of writing this, but you can say like t is 1 over x, so that negative t squared dx equal to dt, but since t is 1 over x, this is negative 1 over x squared. Dx is equal to dt. A lot of ways of seeing that. Anyways, making this substitution, we get the integral from somewhere to somewhere of a fractional part of x. Now, t to the s minus 1 will turn into 1 over x to the s minus 1, which is x to the 1 minus s, because 1 over x is x to the negative 1, so it negates the power. dt is replaced by negative x to the negative 2 dx, because 1 over x squared is x to the negative 2, obviously. The negative I'll pull out in front. Now, 1 over 0 is infinity, and 1 over infinity is 0, right? So we can, of course, switch the order of the limits here by negating the whole thing, so that negative takes care of that, and it turns into this. Also, in the power, 1 minus 2 is negative 1. So one way we can write this, actually, is x to the s minus 1, or s to the negative s minus 1. Now this kind of sounds weird, but what's interesting is you can think of this as the Mellin transform of the fractional part of x, right? Instead of t, I'm using x here. But notice we want this to be t to the s minus 1, not t to the negative s minus 1. But what's weird is if you just kind of think of this from like a function perspective, we're replacing s with negative s. So in fact, you could think of this as replacing s with negative s in the Mellin transform, because the Mellin transform, of course, is in terms of the variable s. The result is anyways. X is the dummy variable in this case. And by the way, I meant to put a dx, not a dt, so sorry about that. Perfect. So that's basically what we're going to kind of be leveraging to kind of not deal with integrals too much and just deal with Mellin transforms instead. Also, what I really want to do is I want to replace this fractional part of x with, what do you think? What we just found out. It's Fourier series. 1/2 minus 1 over pi times that sum. There we go. I had to create some room there, but there we go. Now, there's a huge issue. We could kind of continue, but there's a problem. And the problem is, if we use linearity to split up the Mellin transform, well, we have the Mellin transform of 1/2. And that does not converge. Well, it does converge for some values of s, but not the values of s we want. Now, something I haven't been talking about is the fact that there are domains here. So for this domain, this is really only valid when x is in between 0 and 2 pi, really any interval of length 2 pi starting at 0. So 0 to 2 pi, 2 pi to 4 pi, 4 pi to 6 pi, you get the idea. But here, this is only valid when the real part of s is in between 0 and 1, which I actually showed in the video where this result comes from. Now, the Mellin transform of the number 1/2 is not valid in that domain, so we can't really use it. Now, what's really interesting, a little mind-blowing, is if you just let it be 0 and just ignore it, basically, everything ends up working out fine. But I'm going to try to show you the actual correct way of doing this. And it's a beautiful solution. It's a fantastic solution. I can't take full credit for it, but basically what we notice is that this way of writing the fractional part of x only depends on x right there. So that's the only time x comes up, when you write the fractional part of x as this entire expression. In other words, if we were to consider something like the fractional part of x minus the fractional part of 2x, what is that? Well, I'm not going to write it all out, but hopefully you can see that we'll have 1/2 minus the sum of that, minus 1/2 minus the sum of the other guy. In other words, the 1/2 cancel, and you end up just getting a subtraction of the sums. And I'll kind of run through that real quickly here. So from the first one, after the 1/2 cancel, you get negative 1 over pi times, well, sine of 2 pi n x over n. And then when you do the same thing for negative fraction part of 2x, well, because we're subtracting, that negative 1 over pi becomes positive. Long story short, you can pull the 1 over pi out because they both have that in common, and then you get the sum from n equals 1 to infinity of the second one, so sine of 2 pi n times 2x, which is 4 pi nx, minus the sum of the other one, which will actually group together. So the sine of 2 pi nx. And again, the reason why the order of subtraction there changed is because the 1/2s cancel and there's a negative in front of these. So the second one's really double negative, so I'm writing that as positive in front. So it's not that hard to verify that, I don't think. Oh, perfect. So now what? So now I'm going to be actually doing this. We're going to be taking a look at, well, taking Mellin transform of both sides. And I think we're kind of good to go. It's going to fall apart really quickly, but we're going to have to see a lot of properties. So let me kind of scoot everything up here. All right, so I've moved everything up here. By the way, I'm going to actually rewrite this. There we go. I think it looks a little nicer like that for some reason. Now, we're going to take Mellin transform on both sides, and there's some kind of detail here, obviously, pulling the infinite sum out, but by linearity ends up kind of being okay. There are some convergence issues possibly you may need to deal with, but I'm not going to worry about any of that right now. So let's just kind of do it and see what happens. Now, if we take the Mellin transform of this side, well, recall by linearity we can kind of split things up, and the Mellin transform of the fractional part of x as a function of negative s ends up being zeta of s over negative s. So there's no real issue there. But just kind of keep in mind that when we take the Mellin transform on the other side, we need to replace s with negative s. So we'll see that. But then minus, because we're taking the Mellin transform of a number times t, in this case x, we have to multiply by that value a, which is 2 in this case, to the negative s, if you recall. And then you multiply that by the Mellin transform of the fractional part of x, which again is zeta of s over negative s, just like this. So it's really nice you can actually pull this out as 1 minus 2 to the negative s, all multiplied by zeta of s all over negative s. Perfect. So that's the left-hand side. What about on the right-hand side? Well, I'm going to take the Mellin transform of both sides, and we're going to split things up and take advantage of a lot of these properties. So let's see if we can do this. So we go 1 over pi times the sum from n equals 1 to infinity of 1 over n is a constant in the eyes of, I guess, x. So in fact, this is going to be Mellin transform of first guy, sine of 4 pi nx, minus the Mellin transform of the second guy, which is sine of 2 pi nx. Just like that. Wow, fantastic. Okay, now what? Well, again, we're kind of using that that property. Where was it? It was this this property right here a bit, where if the inside is a multiple of t, in this case I'm using x, but if it's a multiple of the variable, you end up multiplying. You get like a scalar multiple on the outside. Well, not quite scalar multiple, but you get the multiple of that number to the negative s. So we're going to kind of see that here. We get the sum from n equals 1 to infinity of 1 over n. Now for the first one, well, what is multiplied by x here is 4 pi n, so we're going to get that, 4 pi n to the negative s, by that property, times whatever the Mellin transform of sine of x is, which again is sine of pi s over 2 times gamma of s. Now hold on just 1 second. Remember, when we're doing this, because it's of x, we have to replace s with negative x. Now, maybe I'd have to show that because specifically x is 1 over t, but it ends up being true actually in general. So maybe I could have wrote that as a property that the Mellin transform of f of 1 over t is the Mellin transform of just t itself evaluated at negative s, but it ends up being true. So you can kind of verify that on your own with a u sub, but it's very similar to what I showed earlier when I showed this result here, so it's kind of okay. So replacing all of the s with negative s. Now notice, well, sine of a negative, the negative pops out because sine is odd. So in fact, maybe we can, I guess, change the sign like this, and then notice we get gamma of negative s, just like that, and then minus for this next one, very similar. So a is 2 pi n in this case. So we get 2 pi n all to the negative s, but again, we're replacing s with negative s, so there we go. And then we get sine of x, Mellin transform sine of x, which is sine of pi s over 2. Replacing s with negative s changes this sign to positive. And then we get multiplied by gamma of negative s, because we're replacing s with negative s. Fantastic. Now, we're essentially done. All we have to do is do some housekeeping, do some cleaning up, and then out will fall the fantastic functional equation. So let's see if we can manage that. So we have 1 over pi, the sum from n equals 1 to infinity of. So if you kind of take a look here where n is, we have 1 over n. We also have n to the s, n to the s. Those are the only places where n comes out on this second part. So we can pull the n to the s out. And we could also pull out pi to the s. Notice actually we have 4 and 2. So we can actually pull out 2 to the s, what we have in common here. And you know, I'm kind of realizing, so this is 2 to the s, pi to the s. I'm going to leave it kind of like this, separate. What I'm realizing is I kind of slightly made a mistake over here when I wrote 2 to the negative s. Remember that we're replacing s with negative s. It doesn't quite affect this because, well, this guy ends up being equal to this, which is zeta of s over negative s. But it does affect that 2 to the negative s. The 2 to the negative s, my mistake, really should have been a 2 to the positive s. Okay, so sorry about that. And how I caught that is the fact that, well, after you factor out this 2 to the s that we just factored out, what ends up happening from this, all that survives is a 2 to the s, and here we pulled out everything actually. We have n to the s, 2 to the s, and pi to the s. But from the first one, we have a 2 to the s. So that 2 to the s ends up surviving, and in fact I want these 1 minus 2 to the s's to kind of cancel out in the end, which we'll see that really nicely actually. So we have that. Notice actually we also have sine of pi s. We have these 2 sine of pi s's that can be pulled out. To kind of keep in mind the signs here, but we can pull out a sine of pi s over 2. We could also pull out a gamma of negative s. So all we really have in these parentheses is that 4 to the s, we pull out 2 to the s from that, so that you end up getting 2 to the s. And then that's actually negative because the sign was negative here. Very good. So in fact, it's negative 2 to the s. And everything from the second term we ended up pulling out, so we just ended up getting a 1 in this place. So in fact, a really nice way of writing everything left in parentheses is just 1 minus 2 to the s. And what you'll notice is that on this side, this 1 minus 2 to the s matches, and we can cancel that out. Now that negative s in the denominator will actually multiply over here to the other side, and these cancel. What do these two multiply to? So we actually saw a property earlier that gamma of s times s is gamma of s plus 1. So this is gamma of negative s, so that ends up being gamma of negative s plus 1, which I'll write as gamma of s plus 1. Okay. Now, it looks like all of this is inside the sum, but in reality the sum is only dependent on n, and that's really all involving n right here, right there. Like this is, these are the only things involving n. So in fact, how can we write this? We write this as n to the s minus 1, sorry. But n to the s minus 1 is the same thing as 1 over n to the negative 1 minus s. Just like that. So in fact, this is the Riemann Zeta function evaluated at 1 minus s. Perfect. So we have 1 over pi, which is pi to the negative 1, times pi to the s. Let me kind of try to group these together here. So this thing here, we have next to it zeta evaluated at 1 minus s. We have a 2 to the s. We have sine of pi s over 2. We have pi to the s minus 1 because of the 1 over pi. and then this is 2 to the s. Perfect. And all we have left on the opposite side is zeta of s. Wow. That took a lot of work, but with use of Mellin transforms, it kind of streamlined the proof, because in reality the proof is just this. It's pretty short in the grand scheme of things, but using the properties of Mellin transforms really does streamline the process. Now, I'm going to talk a little bit, just a little bit. I know this video is probably being super long at this point, but I want to talk a little bit about some implications, some very important implications. One result I'm not going to talk too much about has to do with the analyticity of the Riemann Zeta function, and there's a property of analytic functions that says that a function that is analytic is actually equal to the conjugate of itself evaluated at the conjugate of that of the variable. So you end up getting something like this. The conjugate kind of pulls out basically. Now as far as zeros go, if rho, let's say, is 0 of zeta, so the zeta of rho is equal to 0, then from this property that I've just shown you now, what we end up seeing is that this is the zeta function evaluated. The conjugate of rho is the conjugate of zeta of rho. But if zeta of rho is a 0, then it's the conjugate of 0, which is just 0. So in fact, we've shown from that property the fact that zeta is analytic, which basically means that it's differentiable over complex variables. If you have a 0, its conjugate is also a 0. And from the functional equation that we just found out here, in fact, I'm going to actually rearrange these in the functional equation. I think it's usually actually written like this. So what we can do is we can kind of grab all this junk here and call it something else. I'll call it, it doesn't really matter what you call it, but I'll call it phi, let's say, of s. So the functional equation basically says the following. It basically says that zeta of s is some function of s times zeta of 1 minus s. So if you have a 0 rho of the zeta function, then that means, well, this ends up being true. And because rho is 0, this is equal to 0. Now it's pretty, not too hard. I'm not going to say it's easy, but it's not difficult. Not super difficult anyways. You have to do some investigating. But it's not too difficult to show that this is actually never 0 when you have a 0 of zeta. Now remember, zeros of zeta are when the real part is in between, the real part of the variable, so the real part of rho in this case is in between 0 and 1. So if you pick a value s that's a complex number whose real part is in between 0 and 1, well, 2 to the s is never 0. Pi to the s minus 1 is not 0. Sine of pi s over 2 is not 0, and gamma ends up not being 0 either. So phi of s is non-zero in that region. Then, well, phi of rho is non-zero. So because this is non-zero, guess what? You have 0 is equal to a non-zero thing multiplied by this. That means that must be 0. So in fact, there's a really nice theorem that we end up getting here. And it says the following. It says if zeta of some number rho is 0, then we actually have an additional four zeros automatically known. We have zeta of rho, conjugate, zeta of 1 minus rho, and the conjugate of that is also 0. The conjugate of 1 minus rho is, well, 1 minus the conjugate of rho. So these three are also all 0. Now a nice visualization of this theorem is the following. So if we have the complex plane, and this, let's say, is the critical strip, where the critical line is when the real part of s is equal to 1/2. So this is the real part of s equals 1/2, let's say. So if you have a 0 rho, 1 minus rho ends up being here on the opposite side, kind of like reflected over s equal, the real part of s equals 1/2. So this is 1 minus rho. and well, the conjugates are just flipping over the x-axis, or the real axis in this case. So there's a row conjugate, and this is 1 minus row conjugate. Perfect. So that's a visualization of these four kind of known zeros. Now, if the Riemann hypothesis is true, then there's really only two that kind of gravitate towards the middle. They kind of get sucked in the middle, if you will, and end up being on the line itself. So that's kind of one big, huge thing that will come up when you attempt to prove the Riemann hypothesis, if you dare to do so. Now, I plan on talking about an idea involving this in a future video, so keep your eyes open for that. But before I end this video, I want to talk about two things, two kind of honorable mentions that have to do with something I've been avoiding throughout this entire video, and that's the fact that when I prove this functional equation, I assume the real part of s is in, well, it's in between 0 and 1. The s is in this critical strip that we've shaded here. Now, if you look at this right side of the critical strip, well, we know exactly how to define zeta here. It's just the sum of 1 over n to the s, where n goes from 1 to infinity. So it's pretty obvious. But on this left side, we don't quite know. I mean, there are ways to extend zeta on this side. I haven't discussed them before, as it turns out. In the critical strip, I've shown you how to do it using the eta function in a previous video. Here, I showed it with the Mellin transform. In the previous video, I showed that as well. But as it turns out, when I proved the functional equation, it assumed the Mellin transform definition of zeta of s over negative s, which is only valid in the critical strip. So what you can do is you can actually use that functional equation to extend zeta to this left side of the critical strip. And that really was Riemann's greatest achievement in some sense. I mean, he did a lot more beyond this. In fact, if you read his 1859 paper, he related it to prime numbers in the kind of way that hadn't been done before, and created what is known as the explicit formula for prime number, while relating prime numbers to non-trivial zeros. And it's pretty marvelous, but it really all has to do with this analytic continuation of zeta onto the entire complex plane. Now, I say entire complex plane, but it's except for at 1. When s is equal to 1, you have a pole of zeta, and that's because when s is 1, this this diverges, right? You get the harmonic series, the sum of 1 over n, which clearly diverges. Okay, so now let's talk a little bit about what happens on the negative side. So first off, there are trivial zeros. And notice, sine of an integer multiple of pi is 0. As it turns out, when n is 0, it will correspond to zeta of 1, which is infinity, as previously discussed. And let me show that with the functional equation. Okay, so I just wrote the functional equation real quickly again. And as it turns out, if we assume this to be 0, where s is on the left side of the critical strip, the reason why I want to assume to the left side is because on the right side we can write it as a sum, and as it turns out, that sum can be shown to be non-zero pretty easily. So if we want to find another zero of zeta but outside of the strip, it must be where the real part is negative. So now with that out of the way, we'll notice zeta of 1 minus s, well, 1 minus s will have a real part that's positive because it's almost like 1 minus a negative is positive. So this is actually non-zero. Positive number to a complex number is also non-zero, so those can be pretty easily shown to be non-zero. Now it has to do with sine and gamma. Now, as it turns out, gamma is not 0 necessarily, but it has poles sometimes. It's infinity sometimes. But it's kind of easy to see when it shouldn't give you an issue, and it has to do with the fact that if s is 2 times a positive integer, well, then you'd have sine being 0. And then this whole thing would be 0, but that would be an issue because zeta of an even number is not 0. We know this because we've calculated this before. In a previous video, I've actually shown this. Zeta of 2 is pi squared over 6, zeta of 4 is pi to the 4th over 90, and so on. In fact, there's a formula that Euler actually proved that zeta of any even number is a number that is closer to 1, but clearly it's not 0. So in fact, this is 0 when s is equal to 2n, but when s is equal to 2n, what happens is that gamma is infinity there, which cancels those zeros. Infinity and 0 kind of like multiplicative inverses of each other somewhat. But anyways, there we go. So what ends up happening is those zeros of gamma end up not being true when you have negative 2 times n. In other words, when n is a negative integer. So I'll just write it as negative 2n. And that can actually be kind of easily shown, because if you have 1 minus negative 2n, this is 1 plus 2n, which is that's gamma of an integer, a positive integer, and we know that's factorial of something, so that's clearly non-zero. A factorial of a natural number is non-zero, so that kind of makes a lot of sense. So in fact, we can pretty easily show that zeta of negative 2n is equal to 0. So they're called trivial zeros because once you know the functional equation, it's pretty easy to show that. So I tried explaining it here, but you can look into like all the details with each of the pieces, but it ends up being pretty easy to verify. Now the last thing I want to talk about here is zeta of negative 1. So as it turns out, zeta of negative 1, if you were to falsely use the summation way of writing zeta, it is 1 over n to the negative s, which is just the sum from n equals 1 to infinity of n to the, I say n to the negative s, I meant to say n to the negative 1, which is n to the positive 1, which is 1 plus 2 plus 3 plus 4 plus 5, which clearly diverges, and so on, right? But it clearly diverges. So this is not the way of defining zeta of negative 1, but we know, in fact, to define zeta of negative 1, we can use the functional equation. So using the functional equation, we have 2 to the negative 1, pi to the negative 1 minus 1, sine of pi times s, which is negative pi over 2, that's negative 1, so that's okay. And then gamma of 1 minus negative 1, that's gamma of 2. And then zeta of 1 minus negative 1, that's zeta of 2. Okay, so let's kind of talk about this for a second. So this is zeta of 2. What is zeta of 2? Zeta of 2 is, well, pi squared over 6, which we've shown in a previous video. It's a very famous result by Euler. It's a result of the Basel problem. This is gamma of 2. Gamma of 2 is 2 minus 1 factorial, which is 1 factorial, which is just equal to 1, of course. Sine of negative pi over 2 is negative 1. And then we have, that's 1 over 2. This is pi to the negative 2. So altogether, pi to the negative 2 and pi to the positive 2 cancel. And 2 and 6 multiply in the denominator to be 12. So what you end up getting is negative 1 over 12 in the end. So zeta of negative 1 is negative 1 over 12. Now, if you haven't seen this before, it's kind of a joke in the mathematics community at this point that it can be shown that 1 plus 2 plus 3 plus 4 and on and on and on is equal to negative 1 over 12. Now, the real correct way of saying this is that the analytic continuation of zeta to negative values would give you that zeta of negative 1 is 1 over 12. But if you kind of falsely use this summation definition for zeta, you kind of write it like that. So you get the 1 plus 2 plus 3 plus 4 and on and on and on is equal to negative 112, which, again, that's not quite true, but you can kind of see that there's a value that relates to that otherwise divergent series. Kind of an interesting idea, but anyways, hope that made a lot of sense. I really thank you all for watching, those of you that stuck around for the entire video. Definitely a lot. I spoke about a lot, and it took a lot of time. So again, I appreciate you all watching. Please, please, please like, comment, subscribe, all that great stuff. If you haven't subscribed already, please do so. It will really help me out. And I'll see you all in the next video. Thank you so much for watching.